Let's now talk about the support vector classifier. The support vector classifier is an extension to the maximum margin classifier, which we talked about before. So it's still a kind of linear classifier, it's a linear decision boundary, but I'm able to deal with a case where the data is not linearly separable. And the basic idea is that before we needed linearly separable data because we needed the points to be all kind of on the right side of the margin. Now I'm saying myself, okay, actually I'm allowed to be on the wrong side of the margin, even on the wrong side of the decision boundary, but I'm kind of keeping track of those violations, and I'm kind of not allowing too many of those violations. So that's kind of the basic idea in words. And if I want to draw a quick picture, so before I had kind of some points, those were the kind of -1 labels, I had the +1 labels, and now I had the decision boundary here of the maximum margin classifier, which was kind of given by this margin here, which is of width 2m in total. So this is exactly what we discussed in the last video. And now I'm saying, if my data was actually kind of different, imagine I had 1 point here and 1 point there. Intuitively, you would say, well, this decision boundary is still a good decision boundary because, well, only 2 points are off. The majority, say another 1,000 pounds, are actually wide outside of the margin. So it looks mostly correct. I'm just kind of violating. So those 2 points give me a violation, in particular if I draw this maybe by a red line. So this point here should have been kind of below this boundary, and it's kind of off by the amount of this red line. It should have really been on the right side of the margin, but it's on the left side by the amount of the red line. Similarly, this green dot is kind of off by so much. So those two red lines are kind of the violations by which I'm off. And the basic idea is that now I'm kind of allowing those violations, but I'm kind of controlling by how much I'm actually violating my condition. So this would be like a violation of the constraint. I'm kind of on the wrong side of the boundary. But the basic idea is, let's just allow it, but kind of keep track of how much and constrain this amount of violations. And let's just kind of work through the derivation a little bit, and let's just start off from what we had last video, where we did the maximum margin classifier. For the maximum margin classifier, we wanted to maximize the margin m over all these coefficients, beta 0, beta 1, and so on. And we had some constraints, so this was subject to some constraint. First of all, we needed beta having length 1. This was mainly for the condition that we could write down the main constraint, which was being on the right side of the margin. So here, being on the right side of the margin means that for every point I, we had to have yi times this beta 0 plus beta vector times xi vector. This would be the ith data point. This thing was bigger equal to m, where m be the margin here. Just recall that if I draw again this picture, so here's the decision boundary, here I have the margin. Now I had, say, a green point here. Let's just focus on the case where yi is equal to +1. It's easier to draw, but the same is true for the other side. So now effectively, so this thing here, this one we derived when we talked about planes earlier. This was just the projected length onto the normal here. So we call that beta is this normal vector here, which kind of defines the plane. And this orange line was just the this length here, basically. This length is the orange line, which is given by this expression highlighted in orange. And what we wanted was that this thing is bigger or equal to m. This difference here is m. And the same for the other side. So we needed this thing to be m, to be on the kind of correct side of the boundary, because for this point here, imagine I had a new data point. So those are all the data points. Imagine I had one here or one here. Obviously, this orange quantity here, the orange quantity would just be calculating this distance here, or here even worse, I will get this distance here with a kind of negative sign. So this kind of, now I will get this distance being kind of minus something, well, it's the distance times the direction basically. So it's here it would be small, but less than m. Here it would be negative actually, and bigger than m. So it would be bigger than m in absolute value. So it would be smaller than minus m in this case. So this quantity in orange is just the distance of this distance from the plane signed, where the distance is positive if I'm in the direction of beta and negative if I'm in the opposite direction. So this is exactly what I did last time, and I know that those 2 points here, which I just draw last, so this point here and this point, they wouldn't fulfill this constraint there. They wouldn't be bigger equal to m. The first one would still be bigger equal to 0, but not bigger equal to m. The other one would probably be bigger equal to minus 3m, but not bigger equal to m here. But I can allow myself those violations if I would introduce a new term here. Say, if I introduce a term here, 1 minus epsilon I in this expression. I'm getting a bit cluttered. Let me get rid of this m here. So if I'm introducing this additional term 1 minus epsilon I, then I can account for these violations if I would have an epsilon I being bigger than 0. So if I have an epsilon I which is bigger equal to 0, I can account for those violations. For example, if epsilon I would be 1, for example, then my constraint up here would just be this thing being bigger or equal to 0. So this point here, it would be fine if I had an epsilon being 1, for example, and kind of this point here would also be fine if my epsilon would be, say, 3, because then I'm kind of 1, 2, 3m on the other side. So and then the condition would be still fine. So these m's here allow me to account for those violations. So here I had this violation here. Here we kind of had this violation here. So those violations I'm now able to account for by introducing this factor epsilon here. If epsilon is positive, I can allow those violations which are marked there in red. So this is basically the way how we deal with data points being on the wrong side of my margin. But obviously, if I leave it with that, I will have I can have as many violations as I like, and then obviously I get a very poor model. The idea is to further constrain it and say, oh, my total amount of violations should be less than some form of budget, basically. And this is the overall formulation of the support vector classifier. I'm maximizing the margin subject to the previous constraints, where now I introduce this extra term with epsilon. Epsilon is sometimes called the slack variable. So I'm allowing myself some slack with those constraints. I can be on the wrong side of the margin by just introducing an epsilon which is positive, because then I'm kind of shifting my constraint to the right here, and then those points which were before on the wrong side end up being on the right side if I shift it. So this is how I deal with violations, but I want to make sure that I'm kind of constraining myself to not do that too much. So I'm kind of giving myself an overall budget of violations. Now you already see that if I would take so this could also be equal, so bigger equal, and this would be lesser equal. It could be less as well. It doesn't really matter. But epsilon could be bigger equal to 0. It could also be 0. In which case, so if epsilon is 0, which I would get if I should b equal to 0. If b is equal to 0, if I have no budgets, then all my epsilon I would be 0, and I'm back at the previous case where I had just a maximum margin classifier. If b would be infinite, then I can violate it as much as I like. I wouldn't get a good fit. But there would be some nice b in between where I will get a good result here. And this is kind of just written down mathematically. So the support vector classifier can be written as a maximization of the margin still with the previous constraint, but where now I'm introducing this additional term, which is the slack variable here, which allows for kind of violation to the previous constraint by effectively just offsetting the constraint. So it's still obeyed by those points which previously were violating it, but I'm kind of putting a cap on those violations by saying, okay, the overall violations all have to be within some certain budget here. So the sum of slack variables must be below a certain budget. And here b, as we already said, it accounts for the flexibility of the model. Small b means less flexibility, high b means more flexibility. Again, we will have some kind of cross-validation where there will be some optimal value of b here, which will tell me, okay, this is kind of the optimal setting here, where obviously it can be, if I choose b equal to 0, if the data is non-linearly separable, then I can't actually find a solution. No solution exists in this case, but if I have some positive b, then I can find solutions, but then there might be an optimal value of b, which kind of gives me the optimal model in terms of test error when I do the bias variance trade-off. Now, it's actually interesting to note that I could rewrite this problem in a different way by kind of formulating it in its dual form or the conjugate form. So I can also write it in this form, which looks a little bit simpler than the other one. Now here c is the conjugate to b, so kind of small b corresponds to big C, and then big B corresponds to small c. Exactly as we had before when we talked about regularization, we had lambda and the conjugate to lambda, which was c. Here we have b and c, they're both conjugates. So kind of how do we get to this relationship? Let's just quickly do the derivation of it in our previous slide here. So this is basically the problem as it's stated on the first slide. This is a kind of optimization problem, but what I can do here is I can just define a new variable omega I. Maybe I should write in blue. I can define a new variable omega I, which is just beta I over m, because beta vector is normalized. So I would then also have effectively, this would mean that I have omega 0 being just beta 0 over m, and I would have omega vector being beta vector divided by m. But now, because beta vector is normalized, so beta vector would be of length 1, but now omega vector would be of length 1 over m. But now we see that maximizing m is the same as minimizing 1 over m, which is the same as minimizing the length of omega. So I can effectively now rewrite maximizing m, I can rewrite it as minimizing 1 over m, or minimizing the length of omega. So this is one way of writing this. So it's effectively equivalent to minimizing the length of omega. So this is this term here. So we already see where this bit comes from. And now I can actually then obviously rewrite the constraint. So the constraint, so beta disappeared now. So there's no constraint on beta anymore, because now I'm talking about omega, and omega doesn't have to be of length 1. It's of length of any length, and I'm actually interested in the length of omega. I'm only left with the second constraint, which is subject to, but now I can take the second constraint and I can just divide it through by m. So if I take this relationship up there and I divide it by m, I will get a beta 0 divided by m and beta vector divided by m, but this is just omega. So I get omega 0 plus omega vector times xi bigger equal to 1 minus epsilon I. The m is gone because I've divided through on both sides by m. So this is just exactly the same as before. And now I have this second problem here where I have n, the second condition, where I have sum over I of epsilon I is less or equal to b, the budget there. So this is now a new way of writing the Boff optimization problem, where now I replaced beta by omega. But this I can rewrite further, because I can take this last constraint here, this constraint, and say that, well, this constraint I can now put into the main optimization problem. This is exactly the same what we did when we talked about regularization. I took this constraint and say, well, actually I can throw it into the main optimization problem by effectively adding it to the objective. So now I have minimizing omega plus some constant times the sum over I epsilon I here. So this would be my new optimization problem, subject to this second constraint, which is the same as before. So this is a new optimization problem here. Let's just try to make a nice box around it, where now I started to move the hard constraint here in terms of B as a soft constraint in terms of C, exactly as I did with the regularization, where now they're inversely related. Because, for example, I know that if I choose B equal to infinite, then this expression here, this thing here, becomes irrelevant. If B is infinite, this hard constraint doesn't do anything, which is the same as choosing C equal to 0, because if I choose C equal to 0 here, then obviously choosing C equal to 0 here means, well, it's not even there, the C. But conversely, if I choose B equal to 0, then effectively I'm just focusing on this constraint, which is effectively, I just want to have all epsilons being 0, which is the same as kind of focusing on this constraint here, which will just kind of put emphasis on this second constraint. So we see that B and C are inversely related, and this expression here is exactly the same as I was writing here. So I have minimizing the length of omega plus this condition here subject to this one constraint. So this is the new kind of way, and this is kind of the way how I can define this support vector classifiers. And just to show you in a little picture here, so here you see a picture where, well, rather than using green dots I use blue dots here, and rather than using red dots I use this violet ones. But here you see that as I kind of shown before, some of those points violate the constraints. So here this point violates, this point violates the constraint, this one as well, this one as well, this one as well, and obviously for the other ones as well I have those points which are violating. So but I'm allowing those violations through the slack variable. So all of those dots with the red lines will require some slack variable epsilon, which is bigger equal to 0. Now if I reduce my budget, I would go to the plot on the right hand side, because now by reducing the budget I'm forcing less violations. I'm making the kind of margin narrower, and now I'm having kind of violations which are a bit shorter, you see here. So the overall length of all the red lines is smaller than the one in the other plot, which means I did this by kind of choosing a smaller b or a larger c correspondingly. So those plots here differ by the choice of c and b here. So this one has a larger b, or conversely a smaller c. This one here is just the other way around. This one here has a smaller b, or conversely a larger see here. Now, interestingly, one thing to point out before we I mentioned that those are the special points which are called support vectors here, which before were in the previous example, we always saw there were 3 support vectors here, which fixed the margin, and only if I change those points was the classifier changing, whereas if I change some point out here, this one wouldn't affecting at all the classifier. But now obviously all those points which violate the margin, they also start influencing. If I move those points further, I'm also moving the classifier with me. So now all those orange points here will be support vectors, not just the 3, but I have more. The 3 which touch the margin, but also all the ones which violate the margin are now support vectors. So here I have, on the left hand side, I have some more support vectors than I have on the right hand side. There's one more. So this is basically a picture for you to see how the support vector machine works and how it works in practice. This is real data, and this is the fitted model here, and you can see the data is not linearly separable, but I can still find this boundary, and in a sense, by choosing a different version of B, I can make it more or less flexible here. So you could think that the left hand side is more flexible than the right hand side, which is less flexible. I can write it down for you. This one here is more flexible, and this is less flexible. And again, I would obtain it by looking at this test error and doing the cross-validation, finding the optimal value of B here, which gives me the best test error, just using standard bias variance trade-off. So this is the main formulation of support vector machines, support vector classifiers. And before moving to the next subject of support vector machines, I just wanted to give a quick comment on the loss function. So actually, I can rewrite this loss function further in this following form here. This is yet another way of writing the loss function. It requires some theory of optimizations of why it is the case, but if you go back, you can already see it from here how I get there. Effectively, what I'm doing here, I'm effectively taking this expression here, I'm solving it for epsilon. So what would this be if I solve it for epsilon? Epsilon I would be epsilon I would be bigger or equal to 1 minus yi times, and let's just call this whole thing here f of xi to be a bit shorter here, f of xi. So this is if I solve for epsilon here, and you can actually show that I can now move this one as well. Similarly, like I moved the B inside of the main optimization, I can move this as well inside of the main optimization, and there it requires a bit more theory to exactly see how that comes about. But what you can do is actually, I can now write this optimization problem is being the minimum. I still have the length of omega here. This optimization is obviously over the omegas. All these optimizations are over the omegas here. And now I have plus this constant c, same as before, sum over I. But now for this epsilon I, I'm effectively plugging this in. But you need to know some optimization theory because of this bigger equal sign and epsilon being bigger equal to 0. It effectively boils down to being a equivalent to the optimization problem where I have 1 minus yi f of xi here inside. And now I've written the last constraint bit and have a fully unconstrained problem. So this is just another way of transforming the optimization problem. Don't worry if you don't understand the very last bit with the maximum. You really have to read up on a bit of optimization theory to understand it, but you don't have to. I don't require you to understand this last step. I just wanted to say that in practice, I often prefer the unconstrained problem, so I will actually use this thing here to run my numerical analysis, to do the numerical optimization. I will use this last bit because it's unconstrained. Unconstrained is always easier to do in practice. And just as a side remark, so kind of I've just derived this relationship here, and it's interesting to see that effectively, if I compare this to logistic regression, we kind of calculated the logistic regression loss function using the maximum likelihood estimator, and we didn't write it out all explicitly, but if you kind of looked at this expression, you can kind of reformulate the loss function there, and you can see that actually it is this. If you plotted the loss function, you will get this shape here, which is this green line, which would be the loss function from the logistic regression. And we see that actually writing it in this form, the loss function from the support vector classifier looks quite similar, and it has this kinky form because of this maximum here. So this so the expression looks like this, and it has this kink here. It's because I have this maximum which gives me this kink. Now you can't see anything anymore, but this maximum obviously gives me a kink at 0 or at 1 exactly, when this expression here becomes bigger than 1, then obviously I will get a 0 value here just by the maximum. If it's less than 1, I will have a linear function here. This is why I have this kinked loss function. That's very similar to the one in logistic regression. Interestingly, kind of you see that this second expression, this is just a very little side remark, this second expression here actually used to be my constraint, and it now became the loss function, whereas this one was exactly the thing I wanted to originally optimize, which was the margin there. But this is now effectively just the which looks a bit like a regularizer here. So I'm actually looking at support vector machines and logistic regression with an L2 regularizer is actually quite similar. The only difference is that they have slightly different loss functions. The one has a kink, the other one has a more kind of continuous loss function here. So this is something I just wanted to point out, and this is just a little side remark. And I also see, which I think obviously this thing here is minimizes things squared. I'm not sure whether I've written it out previously exactly. So this so this thing can obviously be, sorry, it can be the length or the length squared. It doesn't really well, both of them work, and I think the most common one is actually the one with the length squared here. It might have been that previously I looked at the length, but in any case, so I could just use length squared or length. But if I use length squared, then it's actually, this term just looks like an L2 regularizer, and was used to be my constraint, now became a loss function, which looks quite similar to the one in logistic regression, but the logistic regression one involves some logarithms, so it was kind of nice and smooth, whereas this one has this maximum, which gives me a kink. And this loss is also sometimes called the hinge loss here, which is quite important in some other areas like in neural networks. And that's all I wanted to say about support vector classifiers. Now we move to support vector machines, which is a non-linear extension of the support vector classifier. So support vector classifier already dealt with arbitrary data. I do not need separable data anymore, but it was still linear. Now I want to see how I can make it non-linear. That's the next step.